Okay, so we're going to be looking at one of the last bits now. We're going to be looking at approximating a binomial distribution. Now, I have got on this graph the actual representations of the binomial distributions. Now, each of these dots represents the probability of that number of outcomes for a binomial distribution. So if I just start off, Rayhan, I'm literally in the middle of talking. I don't know why you're starting a conversation. So this blue one here is where the probability is 0.5 and there are 20 trials. So you can see each of these dots is representing the likelihood of that occurring. Obviously, the peak is in the middle at 10 because that's what we would expect to be the most likely thing to happen there. Now, these dots are discrete because when you do a binomial distribution, you can't have an outcome of whatever this experiment is and getting 3.67. You either get 3 or you get 4. So at the moment, these are all dots, but what we're going to try and do is blend this from being discrete into something that is continuous, right? What we should be able to notice here is some of the different things that we've got. When we have a small number, so when n is equal to 20, these dots are kind of quite like jagged as you go between them. They don't look very smooth. That's when the number of n is quite small. That the points make, if you were to do them like a dot to dot, they're not exactly smooth, okay? The other thing that we should notice here is that when the probability is 0.7, so it's away from 0.5, we get this kind of distribution. I'm going to just draw over the top of this, which I shouldn't really do. But if I draw over the top of this green one for a second, really carefully, and it's only got 20 trials, does this green one look like it could be a normal distribution? What makes it look like it could be a normal distribution? The peak and the bump. Is it symmetrical though?
No.
It's not symmetrical because remember in this trial when there's 20 things it goes from 0 all the way to 20. So if it was symmetrical we would expect the bump to be at 10. Okay, the bump is not at 10. So the reason this one is not going to, we can't use the normal distribution on this one here is because of this thing. Because the probability is 0.7. What it does is it takes the hump of that shape and it shifts it to, well, it shifts it to the positive end because the probability is higher of that happening. So this one, I will not be able to do a binomial distribution for it. The green one is not going to be good for a binomial distribution. The red one has got a normal distribution, thank you. This one will not be good for a normal distribution. This red one that I've got here has got a lot more dots. And if I was to join those dots together, it would be a much nicer representation than the blue ones joined together. It would make a much smoother kind of curve. So this red one would end up as being actually quite a good approximation if we use the normal distribution instead of the binomial distribution for this one. So this one is not so good, and the reason that the blue one is not so good is because 20 is a small number, so it makes it quite jagged. Whereas this one at the bottom is good because the probability is somewhere in the middle at 0.5, and the number of trials is quite large. So let's just have a quick look at what I've written down here, and we'll explain that a bit more as well. The graph shows the probability function for different binomial distributions. Which one resembles another distribution, and what distribution does it resemble? So we've said the one that we think is the best resemblance is the red one. When p is close to 0.5 and n is fairly large, it resembles a normal distribution. Out of those three graphs that we've got, the red one looks the most like the normal distribution. The p equals 0.5 results in the distribution being symmetrical. For example, if it's a fair coin toss with 10 throws, we're just as likely to get one head out of 10 as we are one tail. So the symmetrical comes from the fact that it's 0.5. However, for this one that I've written down here, if I only had 10 throws, that would be quite a jagged one if I were to join it together. If it had 1,000 throws, then it's something that I would be able to smooth out into a normal distribution. And you're probably thinking, I don't care. Why would I want to change a binomial distribution into a normal distribution? I'm going to tell you a bit more about why we actually do this and what's the reasons for us doing this. So the reason that we tend to use a normal approximation, I'll come back to this bit at the top in a second. The reason that we tend to use a normal approximation if we have this is because the tables for the binomial distribution only go up to n equals 50, so not a very large number. And your calculator will reject large values of n. So if you were to do the binomial distribution with like 1,500 as your value of n, your calculator is going to really struggle because there's a lot of computation in for that. The reason is because the formula for binomial makes us use factorials, and factorials of large numbers cannot be computed efficiently. If you were to type in 65 factorial, for example, your calculator will hesitate and really slow down. Now, if you were going to try and think how many factorials you would need to be able to calculate a binomial probability where x was less than or equal to 65, your calculator is going to get pretty tired. And if you imagine that you were doing statistical analysis for huge organizations or trying to make data inferences about like entire countries of people, you can't keep using the binomial distribution. You have to try and change it to something that is going to be easier to compute and will save time, money, electricity, all sorts of things. So that's why we actually do this here. Okay, so now let's actually think about how this works. If we're going to use a normal distribution to approximate a binomial distribution, it makes sense that we set the mean and the standard deviation of the normal distribution to match that of the original binomial distribution. So the mean of our new normal distribution will be the number of trials multiplied by the probability. That makes sense, okay? If you were going to think about you're going to flip a coin 100 times, you would expect the average. Actually, that's not a very good example. Yeah, that is. You'd expect the average number of times it would be on heads or tails to be 50, because it's the probability of 0.5 multiplied by how many there are. So we'd say if there are 100 trials and there were 50, the average number that we would expect would be 50 heads or 50 tails. The value for the standard deviation we calculate, the standard deviation is the square root of the mean multiplied by 1 minus the probability. Okay, that's something that we just need to know. That is how the standard deviation is found from the number of trials and the probability that there is. So this is something here that we need to have memorized. And actually, it's kind of easy to memorize this, and I'll show you how it's going to be easy in just a second. So far, a summary of what we've said is that if n is large, and when I say n is large here, there's no rule. There's no like, oh, n has to be bigger than 50, but if it's 49, you can't use it. It just is saying it has to be kind of big.
Not 10, basically.
It can't be 10, but maybe 40, maybe 50. It just needs to be big. And it also says that p has to be close to 0.5. Well, 0.45 is close, so that would be probably pretty good, but maybe 0.3 isn't that close. But it kind of is just going to come down to you to decide whether they're close enough, or, hint, hint, if the question says using a suitable approximation, it just means do this. Okay, so if you ever see a question that says using a suitable approximation, it's telling you change it from binomial to normal. Then what we can do is rewrite the binomial distribution where x is distributed binomially with n trials and a probability of p can be approximated by the normal distribution. So it is distributed normally with a mean of mu and a variance of sigma squared where mu is np. Yeah, and then you find out what mu and sigma are by using these things that we have right here. Yes, Ismail.
You said binomial is for discrete data.
Yes.
And normal is for continuous.
Yes. That's exactly what I'm going to talk about on the next slide, okay? Because you're right. How do we take something that is discrete and then use something that is continuous for it? Very, very good question. So just watch out for what happens on the next page with that. Yes?
So you know how it says the sigma is square root of that?
Yes.
Thing. So if you did the square root, you'd end up with the variance.
Yes.
Basically.
Yes, so if you just do them together, you just get the variance, okay? So I'm going to do these ones really quick, and you're probably going to spot how I'm doing these things. So this one is n, and this one is p. So to figure out, we're going from x. We tend to use x for binomial, and we tend to use y for normal. So I'm going to approximate this binomial distribution. Now, it doesn't have a very large n here, and the probability is probably not suitable. But just to say, if we were going to be applying this formula, what it might look like, we would say that y is normally distributed. Well, the mean is just 10 times 0.2, which is just 2. And then the next bit is going to be 10 times 0.2, which is this bit, multiplied by 0.8. So you're going to do 2, the previous thing that you've had, multiplied by 0.8, which is 1.6. So it's going to be 2, 1.6. And we just leave it as 1.6.
Do you not need to square it?
When you put it in your calculator, you square root it. But if you remind yourself about how you write a normal distribution, you always write the variance there. But your calculator, you always put in the sigma, which is the square root of that. So you've got 2 and 1.6. So I found that really quick by multiplying them. And then for the next part, multiplying it by the remaining part of the probability. So the next one, I'll have 20 times 0.5, which is 10. And then I'm going to multiply the answer that I've just got by the remaining part of the probability, which is 5, because it's 10 times 0.5. So I have 10 and 5 here. It might be worth noting that sigma in this case is the square root of 5, and sigma in this case is the square root of 1.6, because both of these things here are the variance, okay? So then this one that I've got down here, to find it distributed, I've got 6 times 0.3, which is completely wrong what I've written, which is 1.8. And then we do that 1.8 and we multiply it by the remaining bit of the probability. So that's 1.8 times 0.7, which is 1.26. So the sigma in that case would be the square root of 1.26. Okay? That's probably how I remember doing the formula. I multiply them together to get this, and then I multiply it by the other part of the probability to get what the variance is. And then obviously I could square root it, finding the standard deviation. So that's how you actually transform it from a binomial to a normal. And now we're going to, I think, on this next page, answer what Ismail's question was. So Ismail said, how can we go from something that is discrete to something that is continuous? And this is something that we call a continuity correction. One problem is that the outcomes of a binomial distribution, i.e. the number of successes, are discrete, whereas the normal distribution is continuous. And actually, if you remember, do you remember with the discrete one, with the normal distribution, we said if the probability that y was equal to, I don't know, 53, what does your calculate, what is the probability that y is equal to 53 for a normal distribution? Something so small that it's actually 0. Because do you remember we said, well, 53 is a very, very specific value. What about if actually the person got, I don't know, let's pretend it was a test mark. What about if someone got, actually a test mark's not a good example. What about if we're measuring heights of something? What about if it was 53.0001 centimetres? It wouldn't be included in that. So the probability of it being exactly 53 is basically 0. So that's why we have to be really careful here, because we're going from discrete to continuous. We apply something called a continuity correction to approximate a discrete distribution using a continuous one. Okay, so let's have a look at this. It says the random variable x represents the time to finish a race in hours. We're interested in knowing the probability that Alice took 6 hours to the nearest hour. How would you represent this time on a number line given hours is discrete? And what about if hours was now considered to be continuous? So if it was discrete on the number line, we would just put a dot to say that, the amount of time was 6 hours, because we've just said to the nearest hour, she took 6 hours. However, we have also want to think about what this might look like as continuous data. For continuous data, we have said that it was 6 hours to the nearest hour, which means that it could have rounded up from 5.5, or it could have rounded down from 6.5. So actually, if we were to change it to continuous data, it would be from 5.5 to 6.5. That entire range would represent the discrete version of it being equal to 6. So in discrete language, x is equal to 6. In continuous language, we're actually saying we're interested if Alice's race took between 5.5 and 6.5 hours. We have to correct the fact that we're taking it from discrete to continuous. So like I've just said here, we can't just find the probability that y is equal to 6 when y is continuous, because the probability is effectively 0. But the probability that y is between 5.5 and 6.5 would seem a sensible interval to use, because any time between 5.5 and 6.5 would have rounded to 6 hours if it were discrete, so if we forced it to become discrete. So whenever you do a binomial approximation, a normal approximation for a binomial distribution, you have to slightly change the thing that you're looking for. You might have to add a little 0.5 on one end or take away a little 0.5 from the other end, just to make sure that you're fairly including the correct probabilities. Yeah, Rayhan?
You know how it's like when it's running, it's like less than or equal, it's greater than or equal to 5.5.
Yeah.
Or less than 6.5.
Yeah, so
Is that less than
technically it would be
equal to-
like that.
Does that make
It makes no difference with the normal distribution because of the fact when you take the probability of a set value, it's basically 0. So it doesn't really matter if we're doing that or if we're doing that. The probability would be like 10 to the power of minus 9 different. It would be like exactly the same thing, really. Okay? So we're just going to think about what these continuity corrections would look like for other discrete values that we've got here. So I've said if x is a discrete variable and y is its continuous equivalent, how would you represent the probability that x is greater than or equal to 5 for y? Okay, so for being greater than or equal to 5, I've clearly put a dot at 5 and a separate dot at 6, 7, 8, 9, 10, all the way up. What do you think it's going to look like if we're now talking about it being greater than or equal to 5 but in continuous? Ronak?
Would it be a dot with a line going over it?
From where?
From 5.
Not from 5. It was not going to be 5 and then infinity. Someone said it, but I couldn't hear who said it. It's going to be from 4.5. And the reason it is going to be from 4.5 is because technically if it was 4.5 or 4.6 or 4.7, if that rounded up to the nearest integer, it would be 5. And you have to apply that in there because it's trying to turn something that is discrete into something that is continuous. So you have to take in that little extra bit there. So the value that we would be looking for is that y is greater than 4.5.
How come we don't shade it in? Because it doesn't matter.
You could shade it in, but it doesn't really matter actually. It could include it, it doesn't matter. I haven't included it, so I haven't shaded it in. But it doesn't matter. It's not actually going to make a difference. So we're now going to say, how would you represent the probability that x was less than 9? Well, look at the discrete version. When it's less than 9, you have to remember how obviously you haven't included 9. You've just got 8, 7, 6, 5, 4, 3, blah, blah, blah. So what do you think the continuous one should be? Muhi, what do you think the continuous should be?
8.49.
Since it's meant to be 9, should be 8.5.
Yeah, so it's going to be at 8.5. Don't worry about the 0.49, okay? It's just going to be here or less. So we're actually saying that y has now got to be less than 8.5. So we changed it from x is less than 9 to x is less than or equal to 8.5, which is in continuous terms that y is less than 8.5. Yeah, what was your question, Muzuki?
I was going to say, why is it not less than 9.5?
Because of this language here, because of it being less than 9. So just reminding ourselves of what we did with binomial before. So a continuity correction is approximating a discrete range using a continuous one. If it has got less than or greater than, first of all convert it to our standard ones, which are less than or equal to or greater than or equal to, like we did here, and then you enlarge the range by 0.5. You want to include just that little bit extra. And I tell you what, every time I do these questions, and I've approximated a binomial using a normal, I forget to do this, and I don't want you to do the thing that I forget to do. So if as soon as you see, okay, I'm going from discrete to continuous, we've got to do this continuity correction that we have here, okay? So there's a few of them here that we should have a little think about. I'm going to give you just super high speed. You don't need to draw any number lines for this. I just want you to say, like this first one, the probability it's less than or equal to 7 will become the probability that y is less than 7.5. That would be its continuous counterpart of it. So I want you to now think, 1, 2, 3, 4, 5, 7 more of them. What do you think that they should be? I'll give us a couple of minutes and then we'll come back together and have a go at these together, okay? Anyone want a chocolate?
Discrete is either one or the other. So you either get 2, or you get 4, or you get 3, or you get 5. So the continuous thing.
I'll put up the next one.
O and you got
Why you calling that simple?
Yo, wait, what is the
Wait, so you know the two,
You're telling me like
the
I have
third
no
last one and the fourth last
I
one?
have no
Yep.
reason.
What's the difference between
I
them?
was asking before.
I thought the difference.
The
is
symbols change.
significant.
The symbols are all changing.
He's never explained this.
So,
It's
so the first one of those would be 3. No, 2.5. No.
But this first one, it's got to be bigger than 3. So actually what we're saying here is it's got to be greater than or equal to 4. And it's got to be less than or equal to... No, I'm not doing anything. I'm not in continuous. I'm still in discrete. I'm still talking about x. I'm saying this is the same as this.
Oh, right.
So then when you go into continuous, we're saying it's got to be greater than or equal to 4, which means 3.5, y, 5.5. And what you can check here is 3.5 would round to 4, so that's good, and 5.5 would round to, would round down to 5. So it does fit, okay?
So then for the second one, you would only convert the 6 to 5.
So yeah, this is now just going to be the probability
3 and 5.
that x is between 3 and 5. Oh, what is wrong with my pen? And me, actually, is really what I should say. So that means the probability that its y is between 3.5 and 5.5. Oh,
Would it be 2.5?
yeah.
And then the last one would be 2.5 and 6.5.
Yeah, because it's got to be greater than 4 and less than or equal to 6. So it's 3.5 and 6.5. Yeah.
No, that's
What?
They talk about me and I'm right here.
I'm not.
We're not.
I'm just putting it out there. I'm not.
Okay. Yes. Yeah.
It's just 0, not possible.
No. You can change that into in a continuous. What round to give you 3?
3.5.
That's it. Okay, so we've got here, this one should be the probability that x is greater than or equal to 10. So it's the probability that y is greater than 9.5. Yes. You just need to, okay. You just need to think about what it's asking for. So here, we're saying that it's got to be bigger than 9. So I'm saying, well, the smallest thing it could be is 9.5, because then 9.5 and above all rounds up to 10. Okay? This one here, we're saying it's got to be less than or equal to, this one's got to be less than 10. So the biggest thing it would be allowed to be is 9.5, because then everything else would round up to 10.
But the top one says it has to be less than or equal to 7.
This one says it's going to be less than or equal to 7, but that's because 7.5 and below all would round down to 7 or equal. Okay, so we're just going to fill in this last one. Shh, shh, shh. Between 1 and 10, what should the probabilities be? 0.5 and 10.5. And then the very last one, if x is equal to 3, well, that's between 2.5 and 3.5.
Why is it not equal to this?
Because anything inside 2.5 and 3.5, if it became discrete, would round to this.
2.5 round to 3 also.
Yeah.
But we don't care about that.
Normal distribution, you don't need.
3, you mean wouldn't 3.5 round to 4?
No, we're 2.5. When you include 2.5 in the thing.
Yeah, but it doesn't matter.
We don't care.
Because we don't care with normal distribution calculated. Because normal distribution, the probability of this... Guys, stop all of this. I can't even hear myself speak to somebody that's like 2 feet away from me. The probability of this is the same as the probability of this when you type it in a calculator. So in normal distribution, they're the same as each other, so we're not really bothered about how they look, okay? Right, I'm going to separate this.
Sir?
Yeah.
How come you did less than or equal?
Oh, because Muzuki was saying, isn't it that? And I said, no, it's because when you put it in a calculator, it's always going to be like this. So if you need to, draw a little sketch of what it looks like, and then you need to make sure you're adding in that little 0.5 or taking away that little 0.5, depending on what the question looks like. Right, I'm going to separate this.